Hi guys, today I want to simulate in depth the Bootstrap driving because it is a very important part of the power electronics, and also because I promised to do that simulation 6 months ago, but I completely forgot it. So let's revise a bit how the bootstrapping works. So basically the problem is that when you have for instance a high side in a like this in a buck converter, you have the inductor, the capacitor, okay. You have to guarantee that this voltage here, so the VG, is higher than the V-switch, the switch node voltage, than at least 5 volts, 6 volts, something like that. To achieve this, you use the technique called the bootstrap. There are other techniques, but the bootstrap is one of the common. So first of all, you supply your system with a logic voltage, let's call it VG. This logic voltage will have a bypass capacitor. This is the logic ground, and we'll draw it like this. Please notice that this ground here is different from the ground here. This is the power ground, and that's instead the digital ground. Now let's get to business. The microcontroller or some kind of logic will generate the PWM. Now you don't care how this PWM is level shifted, but let's suppose just because I want to change topology, let's suppose that this is a common gate level shifter. The common gate level shifter has the gate clamped to the power supply, like this, and the signal is present in the source. So this signal here is not in the gate, but it's in the source. Why do you want to do that? Because the common gate topology is faster than the common source, because of the parasitic capacitances, and also because it is a non-inverting configuration. So when you buy translated level shifters, they probably use the common gate configuration. Now let's change a bit of color. We have the diode and the bootstrap capacitor connected to the V-switch. This is still connected to the same ground as the logic. Resistor R1, and then the NPN pair, the totem pole output. This is connected to the switching node, like this, and the emitter of the NPN, Q1, Q2, is connected to the gate. Now here you can add resistors, diodes, whatever you want. In LTSPICE I can do that, but let's stick to the basic circuit to understand what is going on. So let's suppose that first you have the turning on and turning off system. So this is the signal which do something like this, of course. Now it's a common gate configuration, and remember that this turns on whenever you have the V threshold voltage higher than the V gate higher than the threshold voltage. So basically, if this is kept constant to, I don't know, 10 volts, okay, and this is high between 0 and 10, naturally this is off, okay, so it is the contrary. But anyway, you don't care what kind of level shifter you use. The question is, the matter is, at first the bootstrap capacitor is not charged, so it has to be charged. So I'm drawing the power supply, the flowing supply. This is important. From the VG, it goes straight to the diode and goes straight here. But now it has to close somewhere. Okay? So in the first phase, the voltage across the capacitor C boot is charged to Vg. Now, what happens in the second phase, during the turn-off phase? The current inside this capacitor would like to want there, but it can't. Because basically there is a diode which stops the flowing. Then it goes here, and it flows right in the NPN. And it goes right there. Now what has happened? During the turn-on period, the switching node voltage, V switch, is equal to V in. But now, the VG voltage... Oh, sorry. Let's call this V1. This has the same name. So this is the charger to V1. Okay? The gate voltage VG is now equal to V in plus V1. Because it is carrying the energy of the capacitor. So now you have that the gate voltage is higher than the switching node voltage of a value that you decide in the power supply there. So basically the VGS is equal to VG minus VS, which is equal to V in plus V1 minus V in. So VGS is equal to V1. If if this condition are met, so if VGS is higher than VTH, and then the VDS is way lower than the VGS minus VGS VTH, you are in the ohmic region. Okay. You are basically here in the ohmic region, and then the MOSFET is behaving like a resistor, which is equal to the RDS on, which is in the order of 1 milli, 10 milli. So basically, we are making sure that this MOSFET works in the ohmic region, and now it is switching. Okay. Now for the turn off is basically the same. But instead of flowing this, he will basically flows into the other path. So he will use this MOSFET instead. Okay. One it is a PNP and the other is it is an NPN. So it's the same. Now let's open LTSPICE and let's see what happens. So this is the logic voltage, VLogic. Let's put it to 12 volts. Now let's use the MOSFET. I guess that we can use something like this for a level shifter. And we need to keep I'm sorry. So let's suppose that we are going to use we are going to use the common gate configuration. So we are putting the signal here. Now the PWM is defined with the duty cycle D 0.5 and the switching frequency of 2050 kHz. We do have 0 and 12, 1 nano, D over Fs, and 1 over Fs. Now the resistor. And the diode. Let's put a Schottky. The Bootstrap capacitor. Cboot. A rule of thumb, which I did forgot. Sorry. The Bootstrap capacitor, the voltage delta V across the Bootstrap capacitor, basically it has a ripple inside it. Okay, something like this. So if the nominal voltage is 10 volts, you can have something like 9.8, 10, okay? A ripple like this. So in order to minimize this ripple by a lot, you have to consider, you can make precise calculation of each charge which is given in the switching cycle to this transistor here. But basically, the C boot must be more or less equal to 10 times the C gate or the Q gate. Okay, so basically you have values of the Bootstrap capacitor I in the range of 100 nano and 300 nanofarad. This is also a good value. Even 100, I never saw this value. 500 never saw them. I saw 300 and 100. Okay, so let's put let's put 100 for now. Let's put 100. Then I will show you what happens if it changes value, because this simulation must hold a meaning. So what's the point in not just using a voltage between a MOSFET like this? You may wonder, what's the difference between this boost converter here, okay? What's the difference between this, making the pulse between the gate and the source, and all of this? Well, this simulation at my left side is a very in-depth simulation, and you can even simulate how much charge do you need in order to, if you need maybe an external totem pole, so you can make a more precise simulation. By changing this transistor, it also changes how much peak current you can give. Naturally, the driver naturally will give you how much peak current you can have, of course. Sometimes engineers do put the totem pole outside the driver. Okay, so let's put this, and let's also close the driver. So just to make it clear, in most drivers, this is all inside. All of this is inside the driver. Okay. Oops, I forgot. Okay, let's make the in here. Classical buck converter with okay, sorry, 12 volts, 4.7 micro, 100 micro, and let's put a load of 1 ohm. Let's put the Schottky here. Okay, I think that everything is fine, and we can run the simulation for just even 10 micro, because I don't care to reach the end. Okay, maybe let's run for 1 milliseconds. Let it charge a bit. Ah, sorry, I didn't pick the MOSFET. Okay, let's pick the first on the list. I don't know why, but if you pick a random MOSFET, the circuit won't work. I'm using LTSPICE for almost 8 years, but I never find out why the simulation does not work if it is a random MOSFET. Okay, let's see if we can take an interval. So as you can see, the circuit is working because we have 10 volts minus the drop. So it is from 12, we are going from 20, we're going to 10. Let's put some nodes and let's run the simulation. So this is the output voltage. Now this is the gate, VG, and this is the switching node, switch. These are important. And this is the node, let's call it VD. Okay. So now what we want to see, is first the VGS. Okay, so let's see the GS, and it is defined as the difference between V of G minus V of S switch. Then we have also to look at the Bootstrap node, so V of VD minus V of switch, and this is the Bootstrap. And then we have to reduce the window. We start from 1 milli and we stop to 1.01 milli. Run. Okay. So let's first see the Bootstrap. As you can see, the Bootstrap capacitor is swinging between in between the 11.9 and 12.8. Now, generally speaking, this is not a problem because the ripple is very low. But if this C Bootstrap begins to diminish, the ripple increases. More ripple, it means less gate voltage, less Bootstrap power. So now if you see the VGS, you have the voltage between 0 and 12. Not exactly 12, but 11.50. 11.50. Do you know why? Because it depends on how much ripple do you have on the Bootstrap. You don't believe me? Let's try it. If I put 50 nano, you will see that now you don't have the VD voltage anymore. I'm sorry. It is this minus V of VD. Ah, come on. This is not, of course. So this is this minus 0.3. Okay, more or less. Yes. So if I put 50 nano, this threshold will diminish. This voltage here will diminish. See? Told you. Now the ripple in the Bootstrap has increased from 11.2 to 30. And so basically you're losing 1 volt from your 12 volts. And so you're losing even here 1 volt. So let's put 25. And now at a certain point, your VGS won't be even enough to turn on your MOSFET. Because the ripple is starting to be very, very high. For this reason, the minimal value is 100 nano. You have nothing to lose to put a value of 100 nano. You should have some space in your board. Okay? If you put more than that, then you risk to slow the system too much. So you can't put 100 micro. It is too much. Because, as you can see, it is, of course, too much. So, let's stick to 100 nano, or even 300 if you want to be robust. Now, it is important also to study the physics of the circuit. So, where this current is going? Did we study it well? I said that this current was supplying the Q1, okay? Was going inside there. Can we see it on LTSPICE? Yes, we can. So, we first analyze this current here. Now, let's look very carefully. The flow of the current is in this direction, is positive in this direction. So we have to follow. So LTSPICE, what is saying? He's saying that the capacitor, the current EC boot is positive, and it's positive in this direction. So we have to flow, it has to flow like this. Now, where it is going? To see that, we can see IQ1 and IR1. Okay? So, let's open this and let's see IQ1. Okay, as you can see, we have our answer. So, as you can see, the current of the C boot, this current here, is positive in this direction, and is all flowing here, in the collector. So IC1 is positive, and all the current is turning on this NPN. Then it receives the waveform, and it turns on the transistor, as expected. So I expect this current here to be the same in the turn on phase, select this, in the turn on phase of my waveform. And it is, because this is the VGS, and this current here is charging your VGS. This is the plateau voltage, and then after that it slowly rises to the VGS. So to make sure of that, as you can see, the current is negative in the left direction. So when I turn the minus here, it will become positive. So all the current here is going inside here. Uh-oh. Uh-oh. Not all of that. Uh-oh. Some current is not going inside here. So where is it going? Uh-oh. Hehe. It is going, some of this current is going even in the parasitic capacitor, so we can't see that. Because as you can see here, we have just milliamps. Okay? And here, we have nothing. Ooh! But anyway, so we are now seeing all the flow of the current and how the Bootstrap works. Now, regarding the voltage, this is our waveform, and what we have here is the same waveform turned up, because of course the Bootstrap is a way to Bootstrap to level shift your waveform. So of course you have the level shifting on the waveform. Now, does your Bootstrap impact on the output voltage? Yes, but not so much. The impact it has because if you have a C boot which is very low, you then have less gate voltage. Less gate voltage means a higher RDS on resistor. There is a graph in the datasheet, graph which is like this, and basically, if you have a VGS, let me write somewhere else. Guys, what is this? Guys, what is this? What is this? Ma perché? What is this? What is this paint? I hate so much Windows 11. What is this? Paint was so beautiful. It is lagging everywhere. Sorry for that. Coming back to the power electronics. So basically, there is a graph in the MOSFETs which does like something like this. Okay. Basically, this is your VGS, and this is your RDS on. If the VGS is high, like 5 volts, then you have the lowest VGS possible, which is what we want to have. I think that we discussed everything. This is the current of the Bootstrap, this is the VGS. We can delete everything, and I think that we can close the video here, because it is working. Now we can, as I said before, you can toggle this guy here, and put instead common source level shifter. Okay, it's the same, but it is just inverted. Okay, so now if I do run the simulation, it is the same, but as you can see, it is inverted. So the VGS now, where it was 12 volts, is now 0, and etc. Okay, nothing new. Like my professor said, nothing new under the sun. And the Vout is always 9 volts. So nothing new under the sun. I repeat. Now you can also tune the voltage of the logic. Of course, there is no need to put 12 volts here, okay? If it is a common source, there is no need to put that. You can even put 5 volts, okay? At the end of the day, you're gonna still have 12 volts, because this voltage here depends on the Bootstrap and depends on the logic. So if I put this to 10, then you will have 10 here. So, nothing new under the sun. I repeat. Okay. So why this simulation is useful? The simulation is useful for 3 things. First, it simulates the peak current required in totem pole for switching performance. Then, second, it's important for designing the Bootstrap capacitor. Okay. And third, better look at the waveform of the VGS. Because you are not imposing the VGS with just like this, okay? You're not imposing the VGS with a voltage source like this, but you are letting your MOSFET do the trick. So if I open the datasheet, as you can see, if we stop and look just at VGS, can you see the Miller and the plateau voltage? It's beautiful. But if you do the LTSPICE simulation with just a buck and you put the VGS like this, you are losing this information, okay? And you are letting your MOSFET, you are charging your MOSFET in current basically. You are giving current to your parasitic capacitance, but you're also giving the correct PWM. And so for this reason, you see the true charge of your MOSFET. So you can use this as a benchmark also to test different kind of curves based on the gate charge that you want. For instance, if I put this, I will expect a completely different gate charge. I can then put different MOSFET. I can't right now, but because there are the nodes. But I could put different MOSFET and see the VGS of the different MOSFET very easily. Now, as you can see, the plateau voltage is completely different. It is in the range of 3 volts. Okay? And also the charge has changed. Also the charge required has changed. So it is a very good benchmark, in my opinion, to test the peak current required, the Bootstrap capacitor, and also the waveform of the VGS. Then, of course, you can even look at the diode, but it is not so crucial in this case. Okay? And why not? The waveform will be always the waveforms. If you want to have a look at it, these waveforms are also very good. That's it, guys. I think that I can close the video here. Thank you for your attention, and see you in the next video. Bye bye.